Welcome back, students. Yesterday we were talking about ring homomorphism. We have seen that because there are two operations involved in a ring, so there we need to verify two properties to claim that given mapping is a homomorphism, and that two properties is that structure, preservance of a structure, that is, if F is a mapping from a ring to another ring, so FA should be FA plus B equals to FA plus FB. And another thing what we need to verify that F of AB equals to F of A times F of B. So these two things need to be verified. Also, we have seen several examples in ring homomorphism. Today, let me tell you what is isomorphism, and then we can talk about some properties and examples. Okay. Once we have a homomorphism means that if there are two rings R1 and R2, and if there exists a map F which satisfies these two properties, then we say that F is a homomorphism. Okay, F is a homomorphism, and we are not assuming or imposing any condition on F that if it should be 1, 1 or onto something like this. Okay. So once we impose some condition like we had in a group homomorphism, then we get the concept of isomorphism of rings. Okay. So there are two things. If F is into map, okay, or F is 1, 1 and onto both, okay, there are two things. So let us write a definition. What is the definition? Let F be a map from a ring R1 to R2. Okay. We say that F is a isomorphism. Okay, if F is an isomorphism, if first F is a homomorphism, and secondly this F is 1 to 1. Okay. So here we are claiming that F is an isomorphism. We are not saying that R1 is isomorphic to R2. Okay. When we say that R1 is isomorphic to R2, then it should be onto also. Okay. One more thing. Also, in addition, if F is onto, then we say that R1 or R2 is an isomorphic image of R1. Okay. Fine. So what we mean here, that is the rings R1 and R2 are isomorphic if there exists a map from there exists a map F from R1 to R2 such that it should satisfy certain condition, that is F is a homomorphism. F is a homomorphism. Okay. Homomorphism. Second, F is 1 to 1. And third is F is 1 to. Okay. That is, it should be homomorphism as well as bisective. Bisective means 1, 1 and on 2. Okay. Sometimes oneness this called injective. Injective. This is a surjective. And together we call bisective. Together, these two together, when we club them, we call it is bisective. Okay. So to show that two rings are isomorphic, we need to prove that the we need to find a map which is a homomorphism, which is a homomorphism, which is 1, 1, and which is R2 also. Three things we need to verify. Okay. So let us move further. So the examples we did yesterday, among them you can verify which are 1, 1, which are on 2. Okay. So next, let us see that some example. Let us take another one example. Consider. Let us consider a map. Consider the ring R, which is commutative. Commutative with 2x equals to 0 for all x belongs to R. Define f from R to R by how we are defining fx equals to x square. Okay, fx is equals to x square. Then f is a homomorphism. The question is that is it an isomorphism? So this is the question. This you can answer. Okay. Fine. Okay. All right. This kind of example, I think yesterday we were talking about the characteristic 2 and all. No? So you can relate this with that. So another example, you can take define map f from Z2 to Z2 by f of n. This is equals to n square minus n. Okay. Then f is a homomorphism. Okay. Homomorphism. Is it isomorphism to? So this is the question. Okay. You can try it out. Okay, now let us see certain properties. These properties, there are properties in your textbook in the form of theorem number 15.1, properties of a ring homomorphism. So they are telling that let phi be a ring homomorphism from a ring R to S, and A be a subring of R, and B is an ideal of S. So they are claiming that the 8 properties holds. Okay, 8 properties holds. So they are very much similar to the proof of theorems 10.1 and 10.2 of group theory. Okay, so you can try them, and some of them I will be doing. Okay, but in a different way. Thing is that just like here, if R is commutative, then phi R is also commutative. That is a homomorphism maps commutative ring to onto a commutative ring. Okay, so if R has unity, okay, and S is non-zero and phi is onto, then phi 1 is a unity of S. Okay, so that is unity get transferred under homomorphism. Okay, so and the next phi is an isomorphism if and only if phi is onto and kernel of this is identically 0. So this so many things I will be telling to you. Okay. Here, if A is an ideal and phi is onto S, phi is a map, okay, from A to S, then phi A is an ideal also. So this phi A should be ideal in S, okay. So these things you can know. Okay. So let us see some properties I will be telling. I think maybe different from them and something from them also. So the result is that, or in form of theorem, we can write if F, okay, F from R to R dash is a homomorphism, then first F of 0 equals to 0 dash, and the second F of negative A equals to minus of F. A belongs to R. So let us see the proof. These are the identical as what we have done in the group theory. Okay, so of the first one I will be in brief while dealing these proofs. So A plus 0 equals to 0 for all A belongs to R. That what we know. Okay, fine. And implies that 0 plus 0 equals to 0 for A equals to 0. Okay, and of course the 0 belongs to R. And this implies that f of 0 plus 0, this is equals to f of 0. So this, because f is a homomorphism, so f0 plus f0 equals to f0. So this implies that 0 equals to f0. All right, by cancellation law in additive group. Fine. Here the 0 dash, they are telling this 0 dash belongs to R dash. And in the future, we will be writing 0 only. The second one, we can see that F plus, sorry, A plus negative A equals to 0. So we can apply F on both sides. And in the right side, we will be getting f of 0, and this is 0 because of the first property. So we have fa and plus f times of negative a. This should be equals to 0. Okay, and therefore f of negative a equals to minus times of f of a. So this proves the property. These two property, very simple property. And the next theorem. So in this, there are two things. A, the homomorphic image of a commutative ring is a commutative ring. B, moreover, the converse need not true. The converse need not be true. The second property is that the homomorphic image of a ring with unity is a ring with unity. Okay, and the converse need not true. The converse need not true. So they are interesting. These are the interesting properties that they are talking about the retainment of the property. So अगर f homomorphism है from a ring R1 to R2 और R1 अगर कम्यूटेटिव है तो R2 कम्यूटेटिव होगा पक्का, मतलब उसको कम्यूटेटिव में ही मैप करेगा. फाइन. कहने का मतलब ये है कि अगर आप ये कहो कि क्या यही चीज आइसोमॉर्फिज्म में फिर ट्रांसफर होगी जब हम जाएंगे, जानते हो ना, अगर एक कम्यूटेटिव नहीं है तो दोनों आइसोमॉर्फिक कभी नहीं हो सकते. तो ये चीजें यहीं से स्टार्ट हो जा रही हैं. आइसोमॉर्फिज्म में होता ही है, बट यहाँ होमोमॉर्फिज्म में भी होता है. ठीक है ना. ओके, फाइन. सो कहने का मतलब ये है कि एक अगर कम्यूटेटिव है दूसरा कम्यूटेटिव नहीं है तो उसके बीच में होमोमॉर्फिज्म एग्जिस्ट नहीं कर पाएगा, है ना. ऐसा है क्या, बताइए. इसका मतलब ये निकाला जाए. हेलो. नहीं, अगर कम्यूटेटिव है तो उसका इमेज कम्यूटेटिव होगा, लेकिन कन्वर्स करेक्ट ट्रू नहीं है. कन्वर्स ट्रू का मतलब ये है कि अगर ये होमोमॉर्फिज्म हो जाए और इमेज उसका कम्यूटेटिव है तो जरूरी नहीं है कि प्री इमेज उसका कम्यूटेटिव हो. मतलब होमोमॉर्फिज्म तो भी एग्जिस्ट करेगा. ऐसे ही केस में, ऐसे बी के केस में है. ठीक है ना, समझ रहे हैं आप. सो लेट अस सी द प्रूफ. So let us take let f from R1 to R dash be a homomorphism. And A, B belongs to R such that f of A equals to A dash and f of B equals to B dash. Okay, where A dash and B dash, A dash, B dash belongs to R dash. Fine. So let us consider that A dash and B dash. This should be commutative, okay, and this should be equals to B dash A dash. No, so A dash is nothing but f of A, and B dash is nothing but f of B, and because this is homomorphism, so we can write f of AB, and because R is commutative, so we can write f of BA. Okay, and again because f is a homomorphism, so we can write like this. Fine. So f of B is B dash, f of A is A dash. So this proves that R dash is commutative. Now see, this implies that A dash equals to B dash, and this is B A dash times B dash equals to B dash times A dash. That is R dash is commutative. commutative. The for converse part, consider for converse part, actually what we need to show, let me make it, sorry, let me make it clear. For converse part, we need to prove we need to prove, or so we need to prove that if R dash is commutative, okay, maybe when we say that if R dash मतलब कहने का मतलब ये है कि अगर ऑन टू है तब आर डैश हम कहेंगे, अदरवाइज तो हम कह नहीं पाएंगे ना। तो यानी एफ आर डैश, इसको हम ऐसे कर लेते हैं ना, होमोमॉर्फिज्म लाइक दिस, ओके फाइन, ओके इफ फाई ऑफ आर, ओके फाई ऑफ आर, बिकॉज होमोमॉर्फिक इमेज की बात कर रहे हैं, दैट इज लेट अस से आर डैश ऑन टू मान लो, अगर नहीं मानो तो फाई ऑफ आर ही लिखो, ठीक है ना। आर डैश इज commutative, okay, then R need not, okay. So this we need to give support this statement. We need to support this statement by means of example. So we can consider a ring R, and this is the collection of elements A, B, 0 and 0, such that A, B belongs to A, B integers, okay, A, B integers. So this 2 by 2 matrix, we are considering set of this 2 by 2 matrix, okay, set of 2 by 2 matrices. So here we see that if you take 1, 2, 0, 0, and then we are taking 2, 3, 0, 0. So on multiplication, we will be getting 2, 3, and here 0, 0. Okay, and again, if you are changing them the role, 2, 3, 0, 0, and 1, 2, 0, 0. So on multiplication, we will be getting 2, 4, and 0, 0. So certainly this is not commutative. These together implies that R is not commutative. Not commutative. Okay. Now we define a map phi from R to. We are defining from R to the set of integers by. How we are defining that any so any element here, A, B, 0, 0, this matrix is mapped to A, okay, under phi, okay. Then phi is A, and onto homomorphism. So homomorphism आप verify कर सकते हैं, ठीक है ना। onto if you are taking any integer, so A in here, so you will be getting this kind of element in R. So this is going to be certainly onto map. Okay, so I am leaving it to you. You can verify to yourself. Okay, here Z has unity. Z has unity. That is one, you know, that set of integers. But R no unity not, but we are talking about the first example, no? Okay, first example. Okay, here Z is commutative. Z is commutative. commutative, but R is not commutative. Okay, non-commutative. R is non-commutative. Fine. So, but even though they are not, R is non-commutative, but its image is commutative. Okay. So next next result, it says that homomorphic image of a ring with unity is a ring with unity. Okay. So let us see the B part. B part. So that is we need to consider that R has unity. So let R be a ring with unity. With unity, and F is a homomorphism okay, homomorphism on R, homomorphism on R. Okay, so they are telling that a homomorphic image, that in that case we need to consider that a phi of R. Okay, so let us take 1 belongs to R. Fine. So this means that this implies that because homomorphism, this is homomorphism. So phi f f of 1 should be member of f of 1. F of 1 should be member of f of R. Okay. Let us say it R dash. Fine. Let us say it R dash. Homomorphic image. I'm considering that's a R dash. So we need to prove that this F1 is a unity of FR, or we can say that it is R dash. All right. So let us take, let A belongs to R such that F of A belongs to A dash and A dash belongs to R dash. Okay. R dash is nothing but FR, F of R. Okay. So now consider we can consider f of 1 times a dash. These they are elements of R dash. Okay, so this we can write f of we can write it as f of 1 and a dash nothing but f of a. So we can write 1 times 1 into a, f of 1 into a. Okay, and this is 1 into a, that is f of a, and this is equals to a dash. Okay, so f of 1 times a dash equals to a dash only, and similarly a dash times f of 1 equals to a dash, we can prove it also, and these together implies that f1 is identity of f of R, that is R dash. Fine. All right. And now again they are telling that the converse need not be true. They are telling that the converse need not be true. And the same example will work here also. For converse, consider the ring R which contains A, B, and the second row is 0, such that A belongs to the set of integers. Okay. Define define a map F from R to the set of integers by this A, B, 0, 0, this is equals to A. Okay. Then F is an onto homomorphism. Homomorphism, okay. Here, Z1 belongs to Z, okay, or you can say like this. Here, 1, we can say B, and here 0 and 0, okay. This is mapped onto इस एलिमेंट को मैप कहाँ किया हमने, इसको मैप किया हम A1 पे मैप करेंगे, ओके. And this one is the unity of the set of integers, okay. But one B00 is not unity of R, okay. Fine. The same example works here. Next. Now, once we have the concept of homomorphism, it is natural to talk about that kernel, okay, as we have done in the case of groups. So next concept is the kernel, okay, kernel of a homomorphism. Kernel of a homomorphism. Kernel of a homomorphism. Let F from R to R dash. It is understood that R and R dash are rings, okay. Be a homomorphism then the kernel of F is denoted and defined by we used to write kernel of F. This is a collection of all those elements of the ring R such that F of A equals to 0, and this 0 should be member of R dash. All right. Fine. Okay. So this is a definition of kernel. So you know that note that since for any homomorphism F, F0 map to 0, so kernel of F is never empty, okay. It is never empty. So next theorem says that now one question is that whether or not this is a subring, okay, subring of as we that we talked about that kernel should be subgroup or something we have talked about in group theory. So natural question is that whether this kernel is a subgroup or not, subring of R or not, okay. Okay, so this is the question. The question is that kernel of F is this subring of R. So I want your reply on it. You can try it out. Okay, try yourself. Try it. Okay, some another interesting property is that let us see. If f from R to R dash is a homomorphism, then the kernel of f is a two-sided ideal of what? R. Okay, this is an interesting result. So let us see the proof. So by definition, that the kernel of f is the collection of all those elements of R such that f of a equals to 0, and this should be in R dash. Okay. So since you know that 0 belongs to kernel of f, so kernel of f is never empty. Fine. So to prove that this is a two-sided ideal, we need to prove that RA belongs to kernel of f, and AR also belongs to kernel of f. Okay. But since we don't know, we have not proved that this kernel of f, whether it is a subring or not, because I left it on to you. Of course, you can verify it very easily. Okay. So we need to prove three things. That is, first thing we need to prove that A minus B belongs to kernel of f whenever A and B belongs to kernel of f. The second thing, we need to prove that AR belongs to kernel of f for two-sided ideal. Where A belongs to kernel of f and R belongs to capital R. And then third is that RA should belongs to kernel of f, where A belongs to kernel of f and R belongs to capital R. Okay, these three things you need to prove. Okay, so these are the claims. Okay, we need to prove. So for the first part, it is very easy to see that if we are taking AB, so f of AB, because f is a homomorphism, so we can write f of A, okay, and then we can write plus f of negative B, okay, like this. And of course, the properties we started with today will gives us authority to write this expression in this form. So now f is 0, this is also 0, so this is equals to 0. This means that A minus B belongs to kernel of f. This establishes the first part. Okay. The second part, if we talk about, we need to take A and R. Okay. So for this A and R, and f is a homomorphism, so we can write like this. And since you know that f of A is 0, as A belongs to kernel of f, so we have what? 0. This means what? AR belongs to kernel of f. And then the third part, similarly, we can write it down, f of RA. So we can write it f of R, f of A. And since A belongs to kernel of f, so we are left with FR times 0. So this is equals to 0, and this implies that RA also belongs to kernel of f. So this completes the proof that this is a two-sided ideal. Okay, this is a two-sided ideal. Fine. And one more result I would like to tell you. You can try it out. Next theorem. It says that if f from R to R dash is a homomorphism, then kernel of f equals to 0 identical is 0 if and only if f is 1 to 1. Okay, f is 1 to 1. So you need to first consider that f is a homomorphism in all the cases, and then you need to suppose first that kernel of f is 0. Then we need to prove that this holds. And again, converse way, you need to consider that f is 1, 1, and then you need to prove that kernel of f is identically 0. Okay. So this is a left as exercise. Okay. Right. So with this, let us conclude the discussion for today.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.